I'm going to continue on with my previous example. My previous example was a hypothesis test for the mean when sigma is known. And in my previous video, I found the standardized test statistic and made the decision using the critical value method. In this example, I would like to look at the same problem, but this time I'm going to use the p-value method. So just to recap, a fast food restaurant estimates that the mean sodium content in one of its breakfast sandwiches is 920 milligrams. A random sample of 44 breakfast sandwiches has a mean sodium content of 925 milligrams. Assume the population standard deviation sigma is 18 milligrams. At alpha equal 0.10, do you have enough evidence to reject the restaurant's claim? All right, the claim in this situation is the null hypothesis because the claim up here states that the mean sodium content is 920 milligrams. So that contains the case of equality, so that makes the claim the null and forces the alternative to be not equal to 920. So in my previous example, we found the standardized test statistic by hand, and then I also showed you how to get this on the TI-84 and Minitab Express. And then I found the two critical values using our level of significance of 0.1. When we have a two-tailed test, we divide alpha in two and have equal amount of area in our rejection regions. I used my inverse normal function on the TI-84 to find the lower critical value, and then by symmetry, the upper critical value is the same value in terms of distance from zero. And then our decision, because our test statistic was greater than this upper critical value, our decision was to reject the null hypothesis and conclude that there was sufficient evidence to reject the restaurant's claim. Now, when you use the p-value method, you will come to the same conclusion. It is not possible to reject using the critical value method and fail to reject using the p-value method. They're essentially the same thing in terms of the decision, whether you choose one method or the other. When you use the critical value method, you are comparing numeric values along the horizontal axis. We're comparing the critical value and the standardized test statistic along this axis. Using the p-value method, we are going to be comparing areas, one area being alpha. Okay, so the p-value definition is the probability of getting a test statistic at least as extreme as the one obtained by the sample. And when we have a two-tailed test, there's a slightly cumbersome extra step that you have to do if you want to find the p-value by hand. I strongly suggest using your technology to find the p-value, but I'm going to go ahead and find it by hand, and then I'll show you how to find it on the TI-84. Well, not necessarily fully by hand. I will be using the normal CDF function that I went over a few chapters ago. All right, so the decision criteria for the p-value method for this particular textbook that I'm using currently is that the p-value, when it's less than our level of significance, you reject the null. Some textbooks and some websites use the case of equality here. Okay, it's somewhat arbitrary, but if you take a future stats class or you're looking online for extra help, you might find that some sites use the criteria that the p-value needs to be less than or equal to alpha. Okay, but using the method that is consistent with the textbook I'm currently using, if the p-value is less than alpha, we're going to reject the null. If the p-value is greater than or equal to alpha, alpha being our level of significance right here, then we're going to fail to reject the null. So how do we find the p-value? Well, to find the p-value, we need our standardized test statistic. And again, I found that in my previous video. So our standardized test statistic, okay, and I want to indicate that that is standardized, was found to be 1.84. Okay, so what we're looking for in terms of an area, you want to keep in mind that the p-value is a probability. It is an area, and so is alpha. Alpha represents the area under the curve that represents our rejection region. All right, so drawing my standard normal curve, and because I have a two-tailed test, I have to divide alpha in half. So I'm going to put 0.05 amount of area in this upper tail and 0.05 amount of area in this lower tail. Now previously in one of my last videos, I found the critical value, the upper critical value, to be positive 1.645. Okay, so this upper critical value, I'll call it CV, was 1.645. Okay, so in my previous video I compared 1.84 to 1.645. 1.84 was further out in the rejection region, so I know my decision was to reject the null. Okay, but now I'm not going to be using the critical value. What I want now is I want to find the area further to the right of 1.84. Okay, so I'm going to darken in this tail here. This area under the curve is the p-value. It's the probability of getting your test statistic at least as extreme as the one obtained by the sample. So where is the extremity? It's further out in this tail. All right, so we want to find the area further to the right. If you wanted to use your TI-84's normal CDF function, we could do that. Okay, this will be a little bit of review for you. All right, turning on my calculator. When you're given a z-score first and you want to find an area, you want to use your normal CDF. So going to the distribution menu, selecting 2. My lower bound in this case is 1.84. My upper bound is theoretically positive infinity, but I'm going to put a 1 with a bunch of zeros. And I'm leaving U and sigma alone because I'm working with standard normal. So this area further to the right is 0.0329. Okay, so I'll just round to 3 decimal places here. Now there is a catch. Because I broke alpha in half, this value here is not the full value. This is actually half of the p-value. Okay, so I'm running out of room here. So I'm going to say 1/2 of the p-value is 0.039. Okay, so I'm comparing 0.039 to 0.05. So to get it back in terms of alpha, I need to double everything here. So in your textbook, it will tell you that whenever you have a two-tailed test and you're finding the p-value, quote unquote, by hand, whatever value you find, you're going to have to double it. Why? Because you are comparing it to half of alpha because you've broken alpha in half. Now the original problem has alpha being 0.1. So to get it back in terms of alpha rather than half of alpha, I need to blow everything up by multiplying by 2. So the actual p-value is going to be 2 times 0.039. Okay, that's going to be our final answer for the p-value. So I can just double that value I have, and that's going to be about 0.0657. All right, so there is our full p-value. Taking a peek at our decision criteria, if the p-value is less than alpha, you reject the null. Otherwise, we're going to fail to reject the null. So here's my p-value of 0.0657, and here's alpha, 0.10. 0.0657 is less than 0.1. When that is the case, we reject the null. Okay? So we saw that previously using the critical value method. One method, you're comparing values along the horizontal axis. The other method, you are comparing areas or probabilities. You will reach the same decision, whatever method you choose. Now, one thing that's interesting about the p-value is that it gives you the strength of the rejection. So if I had tightened up my alpha, in other words, I demanded more evidence to reject the null, and I instead decided I want to use alpha being 0.05, my p-value would stay the same because I haven't resampled. Is 0.0657 still less than 0.05? Well, in the universe that we work with in math, no, it is not. It is now greater than or equal to 0.05. So my decision now has changed. My decision when alpha is 0.05 is to fail to reject the null. So it is possible to reject at one level of significance and fail to reject at another. That can happen when your standardized test statistic and critical value are somewhat close together. Now, to get the p-value directly using your calculator, if you don't want to mess with all of this doubling, breaking alpha in half and doubling it to get the p-value, your technology, specifically your calculator, will give you the p-value correctly if you tell it that it's a two-tailed test. So going back to my stat menu, right arrow over to tests, and selecting z-test, that's the appropriate statistical test in the calculator for this example. I have the summary statistics. I want to put in my claimed parameter and my assumed sigma, and my sample mean was 925, sample size was 44. Now, if you select the correct alternative that matches the problem, it will output the correct p-value. The test statistic will not change whether or not you have a single-tailed or two-tailed test, but what will change is the p-value. So you definitely want to set up your null and your alternative correctly. Oops, I've done something wrong here. Let me go back to my stat menu. Oops, I meant to put 18, not 8. That's going to make a difference. Typos matter. All right. All right, so here's our standardized test statistic, 1.843. And look at the p-value. It's 0.0654, okay, rounding to 3 decimal places. And that is reasonably close to what I got when I used the normal CDF function. All right. Now there is a little bit of rounding when you choose to use the normal CDF option, But if you take a look at this p-value, it is still less than 0.1. It will not change the decision. If you decided to use your standard normal table instead, you might even get more of a discrepancy. So I strongly suggest that you do use your technology to get your p-value. To get the p-value in Minitab Express, please look at my last video for this example for Minitab Express. The output does give the p-value correctly.